My goal with these videos is to supplement the topic material where needed and provide a Dr. Tom approach to the solution of selected examples in support of participants in our Mechanical Engineering PE exam review courses. If you have not already done so, I invite you to go to our website where you will find other free videos and information about our review courses. There are several course formats to fit your exam preparation needs. And you can contact us at info@drtomsclassroom.com. Okay, let's get started. This instructional companion is on the method of joints in contrast to the method of sections. This is example 45.8 in the MERM. And a joint is referred to as or drawn as just a solid dot here. Because remember, a truss, a truss is made up of only two force members, so we can get by with, at least at this point, with just drawing the members as straight lines here. You're given 50 feet, and you're given this sort of bizarre 21.65 feet, and of course that got my curiosity. Well, if you do the trig here, what happens is this is 37.5 feet exactly. Okay, so I don't know, I would have probably used that instead of the 2165 here. Now, in the solution that's presented, a nice solution for the method of joints, although there is not time in the PE exam, so I'm going to suggest an alternate problem here, but let's at least get the things that were done in the MERM. First, what they did is they started here over at joint A. Of course, that required finding the reaction at A, which with the 2,000-pound force here in the middle, just by symmetry, that would give you 1,000 here and 1,000 there. So that didn't really take too much. And then what we have at A is a pin, and from there they found AB and AC, those two forces. Then proceeded up to B, and at B, now that we know AB, they could find FBD and FBC. And then, because of symmetry in the loading and the geometry, they invoked symmetry that this force and that force were the same, this one and this one were the same, and that one were the same, which is true, and they were done. Okay, so let me kind of summarize that here shortly. So again, that was kind of quick, so let's summarize again what we did, what was done. They started at pin A, start somewhere where you have only two unknowns, but the reaction at A was an unknown, so they had to go in and find that reaction at A, which of course turned out to be by symmetry as well, 1,000 pounds. And then they applied equilibrium at A. There's only two equations, two unknowns, found FAB and FAC. Then they went on, proceeded up to B, where now with this they only have two unknowns, so at B we got FBD and FBC, and then invoked again symmetry that these two were the same, those two were the same, and those two. Okay, well, and then they provided a summary diagram, which is on the next page here. Okay, this is the summary diagram they provided, although the diagram in the MERM has all these arrows here, which I've been doing this a long time, over 30 years, and I still don't understand those arrows. I mean, somebody gives me a diagram with that, and oh, I don't know. But they already had the C. They got 2,000 compression, 1155 tension, 1732 tension. So you only got T or C. You don't really need the arrows. If you're being confused by those arrows, join the club. If somebody wants to use them, that's okay. But no, T or C will be just fine here. Okay, so but realize that in the PE exam, you certainly, if you wanted FBD up here, you couldn't start here at A and then go up to B. That would be way too much. I think the more likely MEPE exam problem would be the following. Okay, let me write that out first. Okay, what I'm going to propose is, suppose that they go on and give you that the force in FAB is the 2,000 pound compression. That's given. Find FBD. Okay. Well, this certainly would be a good use of the method of sections. Make a cut through here and cut only through three members. But now you've got to draw either this piece or that piece based on what you're going to have to do. You're going to need the reaction at A. No, if all they wanted was FBD and they gave you FAB, then the method of joints, but right at pin B. Again, the joint is it's kind of a, you almost could call this the method of pins. The joint is members coming together at a pin, but remember the members have already been analyzed and they're two-force members, so you don't do any more equilibrium on them. The only thing you can do equilibrium on are the pins. So it's sort of like you're looking at a pin, but that's a joint. So some people call it method of pins here. Well, okay, let's look at all you need to do is just look at pin B, and you'll have only two unknowns. You'll have that one, and you can solve for FBD. So let's see what that looks like. Okay, I've kind of done a lot of drawing here to save YouTube time, but the way in which I do this, I sort of draw the pin at B. I then draw the members. I know that seems like it's extra effort, but it really doesn't take that long, and you can now see the tension or compression. You're given, again, FAB is 2,000 compression, so put it in compression, and then you now know Newton's third law says the 2,000's got to be that way, and you can put the direction on that force 30 degrees down here. Then up here, if it's an unknown member, I make it tension. I don't even think about it. You can think about these and look at them, but no. If it's unknown, I put it in tension. The process will tell me whether I'm right or wrong. Every time you try to put one on here in compression, you will shoot yourself in the foot, believe me. Okay, so we've got this one's in tension, so therefore out, so therefore FBD is to the right, the arrow there. Down here, tension, again, FBC is in that direction, and the direction of FBC is given by this down here. And I then take, and once I've got that drawn, I kind of come in here and cloud around what I'm going to apply equilibrium to. Again, kind of focus in. Now you could just draw that, but the thing is, to me this doesn't mean anything to me until I see that. This doesn't. I have to sort of draw these members in my head in order to figure out what they mean. Well, that's not a very good place for me. I don't know about you, but that's not a good place. So drawing them in here doesn't take that much time. Okay. So now you got an free body diagram. You got two equations. This is concurrent forces. No moment's going to be applied. Some of the forces horizontally and vertically will get your answer. So let's do that. Okay, applying equilibrium. I use this sort of very short-handed symbology here in another one of my MERM instructional videos, companions. Compound beam. I use sum of the forces equals 0, positive to the right, but this is much simpler, and this is sort of a symbol that says sum all forces horizontal, set them equal to 0, make positive to the right, so all of that's kind of locked into there. And so if we look at our free body diagram, just the pin, we've got 2,000 times the cosine of 30, we've got the FBC times the cosine of 60, and then plus FBD equals 0. I'm going to call that equation number 1. And then this is again my symbol for saying similarly to this one, sum all forces vertically, set them equal to 0, make positive up. Okay, so this one has 2,000 times the sine of 30, and then minus FBC times the sine of 60. FBD, of course, only is horizontal, so that's equation number 2. So you can see why they could have given you FAB and asked for, or they didn't ask for FBC, because you could find that by just this single equation here. No, we need to realize that you need to do both of them, find FBC, put it back in here, and now you can find FBD. Okay, so let's solve this equation number 2 for FBC. Okay, so what we're going to do is just take this to the other side, divide both sides by sine 60, and what you end up with is 2,000 times sine 30 divided by sine 60, and you do the arithmetic, you get a number very close to 1155, which of course is what was gotten in the MERM solution. But notice that you've gotten a positive, so the assumption that you made of tension is true, and so, yep, that's how you do it. Okay, you came out with a positive. You came out with a negative, then what you have is negative tension, which is compression. Okay, well let's take this answer and go back to equation number 1 and solve for our FBD. Okay, we'll do this in several steps here. We don't lose anybody here. Well, if we just solve for FBD, we get the minus 2,000 cosine 30 minus FBC cosine 60. Now remember that in doing this, substituting FBC, whatever you got FBC, in this case we got it as positive, but if we'd gotten it as negative, you got, put it in here, okay? So, then both of these are negative, so I'm going to put a negative here and put a bracket around so that we end up with 2,000 times cosine 30 plus the 1155 times the cosine of 60. And so we end up with is, and I kind of do two terms here, 1732 pounds plus 578. I'm going to give myself some breadcrumbs here. And so I've now got those two minus 2310 pounds, and I assume tension. So what I have is minus, but it's tension. Well, minus is equal to compression. So we got now 2310 pounds compression, which again is what was gotten in the MERM. Okay. There is, again, no need to make any assumptions. Look at the diagram, sort of try to figure things out. Once you have all the answers, then you go back to your summary diagram and begin to say certain things or draw certain conclusions. Let's do that. Okay, so once you have your summary diagram, you can sort of look at it and say, okay, well, this is pulling down. Oh, okay, I can see that's sort of trying to push this in at the top. These will be in tension, kind of pulling down. These two are pulling, and that's going to try to make that kind of compress. Yep, those two. So these four are in tension, and these three up here are in compression. Yeah, that makes sense. And then what you're going to do is put this up on your wall if you're designing this truss, and it'll be something that you can have in front of you as a design. For trusses, the biggest problem is buckling, and so you design, and if you're going to make them all out of the same thing, you look for the biggest compressive member. So that's what's going to determine the size of all the other members. There is that one. That's why I'm actually going to try to find it, is because that's the key member. Okay. Well, I think that's a much better problem for the MEPE exam. You might have something different if you're taking a statics course, but that is certainly the MEPE problem. Okay. Again, I invite you to visit our website as part of your exam preparations, and if you have a question about our courses, please contact us at info@drtomsclassroom.com. Thank you for your time, and it has been a pleasure.